everyone. Welcome to our Chapter 9 review session. In today's video, we are going to summarize everything you need to know about parameter estimation, confidence intervals, proportions, t-intervals, and hypothesis testing. This chapter is very important because it connects the ideas from earlier chapters like sampling distribution, and prepare you for real statistical inference. So my goal in this session is to explain the concepts clearly and give you practice questions. I want to start with parameter estimation. So the very first concept is point estimation. Let's talk about point estimation. A point estimation is just a single number calculated from your sample that approximates unknown population parameters. For example, the sample mean estimates the population mean. Sample proportion estimates population proportion. But sometimes the parameter is not mean or proportion, so we need general methods to estimate it. The two main methods we use in this chapter are method of moments and method of maximum likelihood, or MLE. So let's start with method of moments. The idea of method of moment is very intuitive. If the sample comes from a known distribution, the moments of the sample should match the moments of the population. So we said first sample moment, it's equals to first population moment. Second sample moments, it's equals to second population moment, and so on. Then after we set first or second or third or whatever, from the sample is equals to first, second population moment, then we solve this equation for the unknown parameters. Let me give you one example. Suppose x, random variable, has distribution where we know that expected value of theta, it's equals, expected value of our random variable is equals to theta hat, and theta here is the parameter. Also, from a sample, we know that mean of that sample is equals to 8. You remember that mean of sample, we show it with x bar. So I know it's equals to 8. Now I'm looking for this parameter here. How we can find this parameter? By using the method of moment, we know that first sample moment is equals to first population moment, 10 sample moment is equals to 10th population moment. So what is the sample moment? What is the population moment in general? If I remove first here, then I can say that, okay, sample moment, let's write it as Kate sample moment, it's equals to summation of xi, and I starts from 1 to n with exponent k, divide by n, which is the number of our random variable. And I show it with m of k, and population moments I show it with mu of k. And what is the mu? It's expected value of random variable x with exponent k. If k is 1, then mu1 is just expected value, e of x. And m1 is just mean because it's summation of xi divided by n. So this is x bar if I'm speaking about the first sample moment, and then first population moment is just expected value. In this example, I have expected value and I have the sample mean. So by method of moment, we know that m1 it's equals to mu1. So we set m1 to mu1. m1 is x bar and mu1 is expected value of x. X bar here is given, it's 8, and expected value is given theta half. So by solving, you know that theta hat is equals to 16. Why I show with hat instead of just simple theta? Because we are estimating the parameter and it's not 16 is not the exact value of this parameter. We just estimate it by the method of moments. Another method is maximum likelihood. This time we pick the parameter value that makes the observed sample the most likely. And because of that, we call it maximum likelihood. How we approach solving the problem and finding the parameter based on the maximum likelihood method, based on the random variable, if it's continuous or if it is a discrete random variable, then we have PDF or PMF. So I have this function f of x1, f of x2, or maybe p of x1, p of x2. Okay, in both cases, if I have PMF or PDF, it doesn't matter. Let's suppose that I have multiplication of f of x1 to f of xn, and this is function L. Or if instead of f I have p, then I have multiplication of p of x1 to p of xn. So no matter the function is continuous or it's discrete. In both cases, I have new function, which is multiplication of function of each random variable. When I want to solve and find the parameter based on the maximum likelihood after finding this function, I need to take derivative and set to 0 to find what is the maximum. But here I need to find the derivative of multiplication of n different function, which is complicated. So instead, I take natural log from both sides. So the next step is to take natural log from L and natural log from the right-hand side. It depends on if it's continuous or if it's discrete, no matter. We take natural log. After we take natural log from both sides, the next step is to take derivative right now. Derivative of natural log is L prime over L, and for the right-hand side, we calculate what is the derivative. We set it to 0 to find what is the maximum, and then we estimate the parameter. Okay, for example, suppose that we have exponential distribution, we have exponential, and these data 2, 1, 3, and 4 belongs to, these are x value from the exponential. We know that the exponential has the parameter lambda. So we are looking for lambda actually. And we have x1, x2, x3, and x4, which is equals to 2, 1, 3, and 4. And we want to estimate what is the lambda here based on the maximum likelihood method. So I know that for each of 2, 1, 3, and 4, x1, x2, x3, and x4, for each of this random variable, there is a function, and the function is for the exponential, and it's equals to lambda e to negative lambda x, and x is positive, right? So I have f of x1, f of x2, f of x3, and f of x4. So function L is multiplication of these functions, f of x1, f of x2, f of x3, and f of x4. And each of them has this definition, lambda e to negative lambda x. After that, the next step is to take natural log. So before I take natural log, I want to just substitute function here. So we have natural log of natural log of lambda e to negative lambda x1. I don't have natural log because I just want to substitute. So here I have x2, x3, and x4. So I have this multiplication. The next step, I want to take natural log. So natural log of L, it's equals to natural log of product of these 4 functions. But based on the properties of natural log, you know that natural log of this term, it's natural log of lambda plus natural log of e to negative lambda x1, and then you can simplify it. So if I simplify, I have natural log of lambda minus lambda x1 from the first one, plus then second one, again, I have natural log of lambda, negative lambda x2, and the third term and the fourth one, again, is natural log of lambda minus lambda x4. And here you see that I have 4 natural log of lambda from the first, second, third, and fourth term. So I have 4 times natural log of lambda. And then here you see negative lambda x1, negative lambda x2, here negative lambda x3, and negative lambda x4. And you can factor negative lambda, the remaining part is x1, x2, x3, and x4. And the left-hand side is natural log of L. We know that the next step after taking the natural log from both sides is to take derivative from both sides. Derivative here is L prime over L, and derivative of the right-hand side, the first term, it's 4 times derivative of natural log, which is 1 over lambda. And then derivative of lambda times x1 plus x2 plus x3 plus x4, definitely it's equals to x1 plus x2 plus x3 plus x4, because we are taking derivative respect to lambda. So we set the equation to 0 and solve it for lambda. And you see that it is obvious that lambda is equals to actually 4 divided by this summation. And we have x1, x2, x3, and x4 as 2, 1, 3, and 4. Summation, it's equals to 10. So here is 10, and lambda hat, it's equals to 4 divided by 10. And in this way, we can calculate the estimation. We can actually estimate the parameter lambda. Now let's move to confidence intervals. A point estimate gives one number. We learned how to find that parameter. A confidence interval gives a range of plausible values for a parameter. The general form for a confidence interval is the parameter that we estimated. So it is estimate plus and minus, and then we have margin of error. And margin of error is quantile times standard error, where estimate we can call it center, and the quantile times standard error we can call it margin of error. So when sigma, or the standard deviation, is known, then for mean equation it's x bar, so center is x bar, and the margin of error it's z of alpha half times sigma over the square root of n. So z of alpha half times standard deviation over square root of n, this part is margin of error, and x bar is center, or its estimate for mean, because we remember that x bar is estimate of population mean. So this is the sample mean. So here in this case, we use z distribution or normal because the population is normal, or n, or the sample size is greater than 30. Then by central limit theorem, we can use z transformation. For example, if I have sample mean equals to, for example, 20.4, and let's say the sample size is 40, and the standard deviation is 6, and I want to construct 95% confidence interval. 95% confidence interval. How can I have the confidence interval? I need center, which is the sample mean, and then I need z of alpha half times standard deviation times over the square root of n. I know what is the standard deviation. I know n it's equals to 40. So what is alpha in this case? Alpha or the significant level, it's here. 95% confidence interval means 1 minus alpha percent, it's equals to 95. So if 1 minus alpha is 95%, means alpha it's 5%, and I need z of alpha half, so half of 5%. And then to find z of alpha half, I can look at the table of normal distribution to find this value, or I can use syntax of R. By using the Q norm of alpha half, I can find z of alpha half. So I can write it as x bar, or center. This is center. Then I need margin of error. To find margin of error, which is z of alpha half times sigma over square root of n. Here I know alpha is 5%. So alpha half is half of this. So right now, to find z of alpha half, I use Q norm of 0.9975, and then it's equals to 0.0, and here it's 975, Q norm of this, then times sigma over square root of 40. So this is the margin of error. I calculate what is this Q norm. Q norm of this value is 1.96, and if I multiply with 6 and divide it by square root of 40, it's almost 1.86. And then confidence interval, actually 95% confidence interval, it's center 20.4 plus and minus 1.86. So the interval is 18.54 and 22.26. Now, if I want to find the confidence interval for difference between two means, then center instead of x bar becomes x bar minus y bar, and x bar is the sample mean for one population, y bar is sample mean for another population. So this is the center part, and then for the margin of error part, again we have z of alpha half, and it's for the normal or when n is greater than 30. Instead of sigma here in the formula, because it's standard deviation just for this specific sample, let's call it x. Now we have a standard deviation for two population. So one of them is for x, the other one is for y. So instead we have square root of sigma of x square over n of x plus sigma of y square over of n of y. And in this way, we can find the confidence interval for a difference between two means. Sometimes instead of building a confidence interval, we want to know how large should my sample be to achieve a certain margin of error. So if we want a margin of error maximum be, for example, equals to delta for given confidence interval, for example, 1 minus alpha, then n, or the sample size, should be greater than or equals to z of alpha half times the standard deviation over delta, and a square of this value. And here again, delta, it's the maximum margin of error. For example, the desired margin of error for us, or delta, it's equals to 2. The standard deviation, it's 8, and confidence of 95%. Then the lowest or the smallest sample size, it's n greater than or equals to z of alpha half. Here alpha is 5%, then alpha half is 0.025 times sigma, which is 8 over 2 square. And to find z of 0.025, I can use syntax of R and write it as Q norm of 0.975 times 8 over 2, a square of this value. If you simplify, you get 61.5. It means that n is greater than or equals to 61.5. And it's the sample size and it's integer, so it cannot be 61.5. So the lowest integer that is greater than or equals to 61.5 is 62. So n equals to 62 at least. We need 62 sample to get 95% confidence interval. When we want to find the confidence interval when standard deviation is unknown, what should we do? Actually, we treat cases differently depending on the sample size and the shape. There are two cases when we have large sample, and by large sample I mean n it's greater than 30 or at least it's equals to 30. In this case, we replace sigma, which is the standard deviation for the population, with sample standard deviation. So instead of sigma, we use S, which is the sample standard deviation. So in the previous formula that we learned, we just replace sigma by S. If you have a small sample, and definitely here n is less than 30. If we have a small sample from even normal population, now we use t-distribution because replacing sigma, which is the population standard deviation, with S give us extra uncertainty. So instead, we use t-distribution instead of normal distribution. So if I want to write the equation, the formula that we want to find the confidence interval for mean with unknown standard deviation, center still is x bar, and then instead of z of alpha half, which is normal distribution, we use t-distribution. So we have t of alpha half and n minus 1, which is the degree of freedom for the t-distribution. And then, because sigma is unknown, definitely we use S over square root of n. And you remember that the difference between t-distribution and z-distribution, which belongs to the normal, is that t-distribution is wider and has heavier tails. For example, suppose that we have a population of 6 different values, and I know that x bar, or the sample mean, is equals to 50. And also the sample standard deviation, or S, is 4. I'm looking for 90% confidence interval. So center here is given. I know what is the center. Then I'm looking for the margin of error. And I want to use this margin of error and t-distribution. The reason that I want to use t-distribution, it's the amount of sample. The sample size is 6 and definitely is less than 30. So I use t-distribution. To use t-distribution, I need alpha, which is the level significance level. Here, alpha is 1 minus 90%, so it's 10%. And I need alpha half, which is the half of 10%, which is 5%. And n minus 1 is degree of freedom, and it depends on the sample size. So n minus 1 is 5 here, degree of freedom. So instead, here you can use degree of freedom as well. So I can write it as margin of error. It's equals to t of 5% and 5 degree of freedom times sample standard deviation divided by square root of 6. How we can find t of 5% and 5 degree of freedom? You can use table to find t of 5% and 5 degree of freedom, or use syntax of R. If you want to use syntax of R, so it is qt and 1 minus 0.05, which is 95, and 5 as degree of freedom. In this way, you can find t of 5% and 5 degree of freedom. Then multiply with 4 over square root of 6. And now you can find what is the margin of error in this case. If you simplify, it's 3.29. So 90% confidence interval, it's center, which is 50, plus and minus 3.29. So 90% confidence interval, it's 46.71 and 53.29. Now let's work on another example. Let's assume a sample of 200 items contains 40 defective items, and I want to find the confidence interval, 95% confidence interval. Okay, the first thing here is the proportion. What is the proportion of defective items? We know that in overall we have 200 items and 40 of them are defective. So p hat here, I use p hat instead of p for the proportion because I have a sample of 200 items. I don't know about the whole population. So this proportion here is just estimate for the proportion for the population. So p here is 40 defective in 200 items. So this is the estimate for the proportion of defective, which is 0.2. And then we are looking for 95% confidence interval. To construct a 95% confidence interval for the proportion of defective items, again, I need center and margin of error. Here we are speaking about confidence interval for proportion, means center is p hat, estimate of proportion. Okay, now I have p hat. Then I need margin of error. For margin of error, because the sample size is 200, then you are allowed to use z or normal distribution. So you have z of alpha half. And then we need sigma over square root of n, but we don't know what is the standard deviation, right? So here I know I need sigma over square root of n, but we don't know what is the population standard deviation. If we already know what is the population standard deviation, then we don't need to estimate it through the p hat. So I don't have this. So instead, I need to use sample standard deviation. So what is the sample standard deviation when I have the proportion? It's not anymore mean, it is proportion. So the formula here is the square root of p hat q hat over n. So sample standard deviation is the square root of p times 1 minus p, which is q, divided by n. So in this way, we can find the margin of error for this question. We already know what is the center, and for the rest of the question, I need to find z of alpha half, which is alpha is 5%, so it's z of 0.025, and it is Q norm of 975. And then we know what is P. P hat is 2.2. So Q hat, or 1 minus P, is 0.8. Then we just substitute to find the final answer. Here it's 1.96. So we have 0.2 plus and minus 1.96 multiplied with 0.2 times 0.8 over 200. And then we find the confidence interval, 95% confidence interval, which is 0.145 and 0.255. Here for this example, we've found the 95% confidence interval for proportion of defective items for one specific sample in population. If I want to find the difference of proportions and confidence interval for difference of proportions, for example, for two different population, if you remember, the previous one was difference between mean. We mentioned X bar and Y bar. Now, if you have two different population and we are looking for the confidence interval for difference of proportion, then instead of P hat for the center, here I have difference of, for example, P1 hat and P2 hat. So estimate for the proportion of two populations, difference of these two. And then for margin of error, again, we have Z of alpha half if the population is greater than 30. And for the standard error, we have combination of two standard deviations. So I have P1 hat, Q1 hat divided by N1 plus P2 hat, Q2 hat divided by N2. So it's pretty similar because it's, the only difference is right now we have two estimate for the proportion and two standard deviation. The question is, previously we learned how to find the sample size when sigma is known. If sigma is unknown, we don't have the standard deviation, how we can find the sample size when we have the proportion of a population? The relation between margin of error when we know what is the standard deviation and the sample is this one. But when we don't know what is the standard deviation and instead we have the sample standard deviation related to the proportion of a population, and n, which is the sample size, actually margin of error in this case is Z of alpha half, and then the sample standard deviation is the square root of P Q over N. This is the margin of error, and I want my margin of error be less than or equals to some specific value. This delta is the maximum. So we can conclude that when we know what is P, then definitely we know what is the Q here. And if you simplify and solve it for N and it's greater than or equals to P, Q, and then a square of Z of alpha half over delta. This is the inequality for finding the sample size when you know what is the proportion of the population. But in case of that, you don't know what is the proportion and still you want to find the sample size. If you don't know what is P, definitely don't know what is Q and the multiplication of P times Q. But the maximum of P times Q is 0.25. So you replace it by 0.25, then multiply with the square of Z of alpha half over delta to find the sample size. The next thing is hypothesis testing. This is the last major part of chapter 9. So for hypothesis test, there are several steps. The first step is to state null and alternate hypothesis. So we need to state H0 and HA as alternative hypothesis. We know that for H0 or for the null hypothesis, always we have one equally statement, like mu it's equals to mu 0. And for HA, it can be mu it's not equals to mu 0, mu is less than mu 0, or mu is greater than mu 0. So this is the first step to recognize which one is valid for the question. The second step is to compute test statistic. How we can compute test statistic? Actually, it depends on the given part of the question. We use z-test for means when sigma is noun or we have a large sample size. So when n is large or sigma is noun, then we use z-test. And what is z-test? Z-test is x bar minus mu 0 divided by sigma over square root of n. Then we have t-test. Again, we can use t-test for mean when sigma is unknown. We don't have a standard deviation anymore. Or the sample size is small, n is less than 30. Then we use t-test. And t-test again is x bar minus mu 0. And in the denominator, because we don't have the standard deviation, we use sample standard deviation. So it's s over square root of n. We have these two test statistics for mean and one more for the proportion. So if we have proportion, then again we use z, and z-test here it's equals to p hat minus p0 over square root of p0 times q0 divided by n. So this is the second step that we need to compute the test statistic based on the problem. The third step for the hypothesis testing is to find a p-value. This is one approach to solve and to check the hypothesis testing, to find p-value. Or we can look at the acceptance region and rejection region. So step 3, it's using the p-value and computing the p-value, and another method is to find the acceptance and rejection region. And in step 3, we compare alpha with the p-value, compare alpha with p-value, or we compare z of alpha with the acceptance region or the rejection region to see that alpha, it's z of alpha, it's in which area. And then the next step, step 5, is to make the decision. So I can say that the hypothesis testing has these 5 steps. So the last one is make decision. Let's work on this problem. It says a computer system historically has an average processing time of 100 milliseconds. So here we have 100 for the average processing time per task with a standard deviation of 12 milliseconds. After a software update, a random sample of 50 task times produced a sample mean of 104 milliseconds. Using a right-tailed test at 5% significance level, test whether the mean processing time has increased. Okay, when you read the question, you see that clearly it says that you need to use the right tail test. Okay, so the first step to solve the problem is to state what is the null and alternative hypothesis. So the null hypothesis here for us is to mu is equals to 100. And then we have null hypothesis. Clearly it says that we are using the right tail. It means that mu is greater than 100. But if we don't have this term here using a right tail, still we know that it is a right tail and mu should be greater than 100 from this sentence, because it says test whether the mean processing time has increased. So mu is greater than 100 and increased. So this is the problem that I have. And by right tail, I mean that we have, for example, a normal distribution or a t-distribution based on the sample size. We have normal because n is 50. And then here basically is 0, and we have a symmetric normal or t-distribution. And when mu is greater than 100, then we are in the right part, and this part is the rejection area. Okay, this is the first step. We state H0 and HA. The second step is to compute the test statistic. Because here n is greater than 30, so we have normal distribution. When we have normal distribution, we use z-test. So we use z-test, and the formula is x bar minus mu and divide by s over square root of n. And s or sigma, here sigma is given. So sigma over square root of n. So x bar for us here it's 104 based on the given part, because it says that the sample mean is 104 and mu 0 is 100. The standard deviation is 12 and the sample size is 50. Now we compute this and we have 2.36 for the second step. The next step is to compute p-value, or if you remember, I mentioned that you can find z of alpha and then compare z of alpha with your z-test value, with the test statistic, and see if z of alpha is greater than this value or it's less than this value. I do both way, so let's find z of alpha. And this point here is z of alpha. Z of alpha is z of, and alpha is 5%. Because alpha is 5%, I need z of 5%. We can compute it by Q norm of 0.95. This value is 1.64 almost. If I want to just keep two decimal places, it's just 1.64. Now our job is to compare z-test with z of alpha. If z-test is greater than z of alpha or it's less. If it's greater than z of alpha, then we are in the rejection area and we need to reject the null hypothesis. Let's see. Here I know that z of alpha is 1.64, so here right now it's 1.64 and z-test is 2.36. So I can say that, okay, z-test from the test statistic is here. And as you see, is greater than z of alpha, and we are in the rejection area because this part is rejection area. So we need to reject null hypothesis. Another way and another approach to solve the problem after finding the z-test is to find p-value. When we want to find the p-value, what we need to do? To find the p-value after we finding the z-test, now I don't know what is the z of alpha. I have the test statistic is here, and now I'm trying to compute the probability of all variable greater than z-test. So if this is my graph, I want to see what is the probability of all random variable greater than z-test. So to find the p-value, I compute the probability of all random variable greater than 2.36. This is the normal distribution, and we know how to find the probability greater than some specific value, 2.36. So it's equals to 1 minus p norm and p norm of 2.36. Because you remember for the normal distribution, when we are computing the probability of random variable less than some constant, for example 2.36, we use p norm. Now all random variable greater than 2.36, so it's complement and it's 1 minus p norm. Now we compute this to find what is the p-value. It's equals to 0.009. So this is the p-value. After we found the p-value, now we compare p-value with alpha. Alpha is 5%. As you see, p-value, which is 0.009, is less than 5%, which is alpha or the significance level. If p-value is less than alpha, we reject the null hypothesis. So it means that there is evidence that the mean processing time increased. So again, we reject null hypothesis. Okay, the next question is, a company believes that 25% of customers experience a minor complaint with their service. In a recent sample of 240 customers, 70 reported a complaint. Now, at the 5% level, determine whether the true complaint rate differs from 20%. Okay, the first step is to state null and alternative hypothesis. So what is the null and alternative? The null hypothesis is the proportion it's equals to 25% or 0.25. And then it says that determine whether the true complaint rate differs from 25. So it can be less or greater than 25. So P, it's not equals to 0.25. Actually, this is a two-sided test. When we have two-sided test, then instead of considering just Z of alpha here and have rejection area in one direction, we have two rejection area, and area in total is alpha. So alpha half is here and alpha half is here. So you need to remember that we have two rejection area, this one and this one. Here is Z of alpha half and here is negative Z of alpha half. Now the second step, we want to compute the test statistic. How you can compute the test statistic? It's Z or T test or proportion. As you see, right now we are speaking about the proportion and the sample size is 240, so we are using normal and Z test for the proportion. So what is the p hat here? We know that among 240 there is 70 complaint. So 70 divided by 240 gives us p hat equals to almost 29 if I just keep two decimal places. Okay, now we want to compute Z test for the proportion. So it's p hat minus, let's call it p0, and in the denominator we have p times q over and under the square root. Now if we substitute, p hat is 0.29 and p0 is 0.25. In the denominator we have 0.25 and q it's 0.75 over square root of n, which is 240. If I simplify, the answer is 1.66, and this is the Z test. Now we have two approaches. We can find Z of alpha half and negative Z of alpha half, and then check that if Z test, it is positive, so I just care about this part, definitely is not negative. So I want to check that Z test is here or here. If it's greater than Z of alpha half, then it's in the rejection area, so we need to reject the null hypothesis. And if it's less than Z of alpha half, then we cannot reject the null hypothesis. Or I need to compute p-value. To compute the p-value, now we have Z test. Let's suppose that, as I don't know where is the Z of alpha half, but here is 1.66. Then I'm going to check probability of all random variable greater than 1.66 and compare it with the 5% level. If the p-value is less, then we reject the null hypothesis. If it's greater than alpha, then we cannot reject. Okay, here I'm going to do both and compare the two methods with each other. If we compute p-value, we have Z test and let's say z, it's here 1.66. Because we have two-sided normal distribution, one thing is to check that if z-test is here and the negative of z-test is here, what is the probability of all z greater than z-test? And then what is the probability of all z less than negative of z-test? So I'm going to find the probability of all random variable greater than 1.66 and less than negative 1.66. So these two parts are equals to each other because the graph is symmetric. So if you find the probability of one part and multiply with 2, then you have the probability of both. So it is 2 times of probability of z greater than 1.66, or 2 times of probability of z less than negative 1.66. And this is equals to 0.097. You see that alpha here is 5%, and 5% is, again, alpha here is less than p-value. So p-value is greater than alpha, which is 5%. And we know that when p-value is greater than alpha, we cannot reject null hypothesis. So we fail to reject null hypothesis. Okay, now second approach. When we want to compute z of alpha half and negative z of alpha half. For the second approach, we compute z of alpha half. Alpha is 5%, so alpha half is 0.025. I use Q norm of 0.975, which is 1.96. It means that this point is 1.96 and this point here is negative 1.96. Now, where is 1.66 respect to z of alpha half and negative z of alpha half? If here it's 1.96, this point is z-test and it's 1.66. These two regions, here and here, they are rejection region, and this is acceptance region, because right now the z-test is less than z of alpha half, and also is greater than negative z of alpha half. It is in the acceptance region, and we cannot reject null hypothesis. So we fail to reject null hypothesis. Next question. A juice bottle is supposed to contain 80 milliliters of juice on average. A sample of 10 bottles is measured. Sample mean is 84 milliliters and sample standard deviation is 12 milliliters. At 5% significance level, determine whether the machine is overfitting. Okay, to solve the problem, the first step is to see what is the null and alternative hypothesis. So the null hypothesis here is given, and it says that the average is 80 milliliters. It means mu0 is 80. And then we want to see at 5% significance level if the machine is overfitting. Overfitting means mu0 is greater than 80 milliliters. Second step is to compute the test statistic. In this case, we have 10 bottle of sample. So the sample size is 10 and is small. And also we have sample standard deviation. When we don't know what is the standard deviation and the sample size is small, definitely we use t-test instead of z-test. So I need to use t-test. And what is the formula? It's x bar minus mu 0 divided by s over square root of n. We have t-distribution. That means that if this is my distribution and I'm looking for mu 0 greater than 80, it means that it's right tail. So this is the rejection area. Here we reject null hypothesis, and here we fail to reject the null hypothesis. Okay, it means that this point is T of alpha. So one approach is to compute t-test and compare it with T of alpha. And T of alpha here is T of 5%. And to calculate T of 5%, remember that when we have t-distribution, it's important for us that what is the degree of freedom. And degree of freedom, it's n minus 1. In this case, n is 10 and n minus 1 is 9. Okay. So the syntax here is qt, and 1 minus alpha is 95, and degree of freedom is 9. Now I need to compute this. Almost is equals to 1.83 if I keep two decimal places. Now, if I compute t-test and I see that it is greater than T of alpha, it means is in the rejection area if it's here. And if it's less than T of alpha, then we fail to reject null hypothesis. So let's see. X bar is 84 and mu 0 is 80. S is 12 and n is 10. So I have a square root of 10, which is 1.054. 1.05 respect to 1.83 is smaller. So t-test is here, and you see that is less than T of alpha. So it means that it's in the area that we fail to reject the null hypothesis. So one approach is because t-test is less than T of alpha, then we fail to reject null hypothesis. Another approach, instead of comparing t-test with T of alpha, is to compute p-value. And p-value is the probability of all random variable greater than this t-test. T-test is here, and I want to see what is the probability of all t greater than 1.054. This is the t-distribution. To compute t greater than some constant, it's 1 minus p t, 1.054, and do not forget that we need to know degree of freedom, which is 9. Now, if I compute this, it almost is equals to 0.16. This is the p-value. And now I want to compare p-value respect to alpha. So let's suppose that alpha, which is 5%, is here. This is alpha. We know that if p-value is less than alpha, we can reject null hypothesis. And if p is greater than alpha, then we fail to reject the null hypothesis. This is 0.16 and this is 0.05. You see that p-value is greater than alpha. So when p-value is greater than alpha, then we fail to reject the null hypothesis. It means there is no significant evidence that the machine is overfitting. All right, everyone, that concludes our Chapter 9 review. We covered method of moments, maximum likelihood, confidence interval with known and unknown standard deviation, proportions and difference of proportions, difference of mean, hypothesis test, p-values, and how we can interpret the result and make a decision. Make sure practice the problem, and thank you for watching and good luck on your test.